Okay, everybody, welcome back. So we've discussed the electrophysiology, discussed the anatomy and the physiology of the cardiovascular system, and it's now time to kind of put those two components together and really take a look at what this translates to into the ECG. We're not going to get into actual rhythms yet, but we're going to get into the components of the rhythm and the graph paper and talk about how all of these components that we've talked to up into this point, how they all come together and actually create waveforms, create ECG tracings. And then once we understand that component, then we can actually start putting this into practice and looking at the rhythms and how to differentiate different types of cardiac rhythms. So let's first talk about the paper and the calibration of the machine. When we talked about electrode placement, we did talk about specifically placing electrodes in their respective areas, whether you're looking at observation mode versus diagnostic mode. And that's because an ECG is actually printing out on graph paper that is calibrated to a standard amplitude, which is what we call the y-axis or the north to south pole, and the time axis, which is the x-axis. And it prints on a calibration. Every time you turn your monitor on and you run a test, you'll see a calibration box that prints out. And it's designed to calibrate to a 10 millimeter amplitude and 0.2 second wide box. And it should print over your graph paper and look exactly as it's supposed to, right? It should be 2 boxes tall and it should be 2 boxes wide. So, 1 large box wide, 2 large boxes tall. And this ensures that your ECG machine is appropriately calibrated to the paper because, believe it or not, there's a lot of math that's involved in ECG interpretation. And this time and amplitude criteria is actually how we categorize rhythms, how we name them, the nomenclature that we use, and how we differentiate which part of the heart we're looking at based on what's occurring. So for a baseline understanding, your amplitude is along your y-axis. Every single small box is 1 millimeter, and every large box, as you can see on the screen here, consists of 5 smaller boxes, and that's 5 millimeters tall. The time axis, the x-axis, looking at left to right of the graph paper, one small box notes 0.04 seconds. With 5 small boxes contained in a large box, the large box represents 0.2 seconds of time, or 1/5 of 1 second. Okay, so now let's talk about the tracings and how they work. So when a line is printed on the graph paper, you have a baseline across the middle where there's no deviation. This is called your isoelectric line, and it represents no electrical activity within the heart. There's nothing changing, nothing's going on. This is the period of electrical silence. We can then look at deflections based on the movement of electricity towards the positive electrode or towards the negative electrode, respective of the lead that we're evaluating. If the electricity is moving towards the positive electrode, you're going to see a positive deflection of the isoelectric line. If it moves towards the negative electrode, you're going to see a deflection negative or below the isoelectric line. You also have complexes that will show up as what we call biphasic, and this is where for a period of time the electricity is moving towards the positive electrode, and for a period of time it's moving away from the positive electrode toward the negative electrode. This creates a biphasic deviation of the isoelectric line. Okay, now getting into the individual waveforms. So we've already seen the small chart that's in the bottom of your table when we looked at the phases of the cardiac cycle and how that translates into various segments and waves. And we're going to go through each of these individually, but I do want to start by having you look at them all together. You can note that we have waves, we have complexes, and we have segments and intervals. All of these components are going to come together to interpret an ECG tracing. But when we look at the fundamentals of ECG interpretation, we really are looking at the interpretation of a single group of complexes. So this P wave, PR interval, QRS complex, ST segment, and T wave, represents the entire depolarization and repolarization of the heart in one cardiac cycle. And an ECG rhythm is a series of these placed together on a graph. All right, let's start with the P wave. The P wave denotes its origin from the sinoatrial node. In fact, when we get into interpreting rhythms, one of the ways that we'll denote whether a rhythm is sinus in origin is the presence of a P wave. Now, there are criteria for a P wave that would be considered normal. And what we're going to go through and talk about today are the normal representations of each of these waves and complexes and intervals. Because once we fully understand normal, then we can look at deviations of normal to find rhythms that are abnormal or dysrhythmias. So a P wave is the positive deflection preceding the QRS complex. Or another way to look at it, if you're looking from the isoelectric line, it will be the first positive deflection of the isoelectric line in the cardiac cycle. Normal amplitude for a P wave is less than 2.5 millimeters. Normal width for a P wave is less than 0.11 seconds. So it should be about 2 boxes tall and about 2 boxes wide, assuming your monitor is properly calibrated. The morphology, when we say the word morphology, we're talking about the shape, the presentation of the shape of a P wave. The morphology should be smooth, round, and upright. And what I mean by upright is a positive deflection from the isoelectric line. Moving left to right through the entire conduction process, the next piece that we come to is the PR interval. And the PR interval marks the time from atrial depolarization, which is your P wave, until the ventricles fire. So your PR interval will start from the beginning of the P wave until the beginning of the next complex, which will be the QRS complex we'll talk about here in a moment. Your normal duration for your PR interval is 0.12 seconds to 0.20 seconds, or 3 to 5 small boxes. Again, remember that your P wave should be smooth, round, and upright, and there should be a period of inactivity between your P wave and your next complex, the QRS complex. The next complex that we look at is the QRS complex. Now, unlike the P wave, the QRS complex is actually broken down into 3 separate waveforms that combine together to make the QRS complex in its entirety. The Q wave, by definition, is the first negative deflection following the P wave. It should be less than 1 millimeter deep. The amplitude should be less than 1, and it should be less than 1 small box wide. The R wave is the first positive deflection following the P wave. And the S wave is the negative deflection following the R wave. Normal QRS duration is less than 0.12 seconds. So from the time that the QRS complex starts until the S wave returns to the isoelectric line, you should be less than 3 boxes wide. Okay, as I mentioned a moment ago, the QRS complex is actually broken down into 3 separate components: the Q wave, the R wave, and the S wave. If you've looked at any ECGs during your career, you'll recognize that not every QRS complex looks like the one on the top left of your screen. In fact, very few actually look like a true QRS complex. So QRS complexes can come in many forms, and we denote those complex by changing around the letters and the capitalization of those letters. This is the QRS morphology and nomenclature. So with defining the Q wave, and we'll start at the top left rhythm or the top left complex there, we note that there is a small Q wave, which is the first negative deflection of the isoelectric line following the P wave. That's denoted by a lowercase q. We see a relatively tall spike, the blue shaded area, from the isoelectric line, which is a large R. So that would get a capital R. The R wave concludes when it returns back to the isoelectric line, the red dotted line that you see on your screen. And then it continues on to create the S wave, the negative deflection following the R wave. And it concludes when it returns back to the isoelectric line. This S wave is small in comparison to the R wave, so we would denote that complex with a small q, a large R, and a small s. Still a QRS complex, but how we capitalize those letters represents the visual representation of that specific complex. The next complex on the top right of your screen is the RS complex. Note the absence of a Q wave. There is no negative deflection following the P wave, but there is a positive deviation following the T wave that starts in the blue shaded area. That is the start of your R wave. The R wave rises up above the isoelectric line, returns back to the isoelectric line, the red dashed line that you see on your screen, and that concludes the R wave. It then continues down to a negative deflection, the purple shaded box. That is the start of the S wave, and the S wave concludes when it returns back to the isoelectric line. This complex is noted as a uppercase R, uppercase X complex, or an RS complex. Next, we'll look at some of the deviations again. Looking at the bottom left of the screen, you'll see what's known as an RSR complex. Following the P wave, the first positive deflection there, you'll see the line slowly sloping upward, the blue shaded box, away from the isoelectric line. That's the first R wave. That R wave concludes when it returns back to the isoelectric line. The line then continues below the isoelectric line, creating a large S complex, and concludes as it returns back to the isoelectric line, which then continues on to a positive deviation from the isoelectric line, creating a second R complex. The R waves are small in comparison to the S wave, and so we would note this as a lowercase r, uppercase S, lowercase r complex. And for the last rhythm on the screen, the bottom right-hand side, this has a positive deviation behind the P wave, noting an R wave, the blue shaded box. It concludes as it returns back to the isoelectric line, where the shading turns from blue to purple, at a large S wave deviating below the isoelectric line and then returning back to the isoelectric line where it concludes its waveform. And this is known as a lowercase r, uppercase S complex. As we can see, there can be great variability in the presentation of the QRS complex, but each of these still represent ventricular depolarization. While your P wave is your atrial depolarization, your QRS complex is a tracing of electricity through the ventricles as they depolarize. Following the QRS is the J point. And the J point exists at the conclusion of the terminal complex of the QRS complex. So looking on the image on the left here, you can see that the ending of the purple shaded area, that S wave on that complex, the S wave makes a sharp deviation back toward the isoelectric line, and there's a period of isoelectric silence or electrical silence along the isoelectric line. That segment, and combined with the T wave, is the ST segment. That point in which the that point in which the S wave returns to the isoelectric line is known as the J point. And identifying that J point is what we will use to identify ST segment elevation or ST segment depression. And that consists of where the J point lands either above or below that isoelectric line. We won't mess with ST segment elevation in this series, but when we look at 12 leads, we certainly will be paying attention to that ST segment. All right, now we're on to the T wave. The P wave, again, represents atrial depolarization. The QRS complex is ventricular depolarization. And your T wave represents ventricular repolarization. This is the positive deflection following the QRS complex. The morphology for the T wave should have a relatively lightly sloped upward direction to the peak of the T wave, and then a sharp decline downward. And we call this an asymmetrical presentation. It slopes up gently with a rounded top and then returns quickly to the isoelectric line. A normal T wave should be in the same direction and the same orientation as the QRS complex, with an amplitude limit of half of the total amplitude of the QRS complex. This means that an appropriately sized and shaped T wave should not be more than half of the height of the QRS complex overall. Now, much like the QRS complex, the T wave can have specific morphologies, and these are linked to various pathologies that we'll discuss further in 12-lead interpretation. On the top left of your screen, you see a normal T-wave presentation, that asymmetrical approach with a quick decline back to the isoelectric line, not exceeding more than 50% of the height of the QRS complex. The next top image in the middle is a tall T-wave. A tall T-wave would exceed 50% of the overall amplitude of the QRS complex. Note that it's still maintaining its rounded structure, but your morphology may begin to change as you change shapes. Top right is a biphasic T wave. This is where the ventricular depolarization is creating both a positive and a negative deflection from the isoelectric line. Bottom left is a peaked T wave. Peaked T waves have a more symmetrical approach and lack the rounded top that you would see in a normal T wave. And the last image, middle bottom, is the inverted T wave, and it's a deflection opposite of the QRS complex. Okay, next we'll talk about the QT interval. The QT interval is the duration from the start of the QRS complex until the end of the T wave, or the T wave's return to the isoelectric line. This represents the entirety of ventricular depolarization, the QRS complex, and ventricular repolarization, the T wave. This is a good way for you to see again the concepts of the refractory periods. Your absolute refractory period is from your QRS complex until the start of depolarization, or the start of your T wave, where there is no storage left for the ventricles to re-depolarize. They can receive activation energy, but they're not going to depolarize again because they're already depolarized and they have not gone through repolarization yet. Your relative refractory period is from the start of your T wave until the end of your T wave. And that's because the ventricles are in the process of depolarizing. All right, to go back and review, the P wave. This is your sinoatrial node, your SA node firing. Normal duration is less than 3 boxes. Normal amplitude should be less than 3 boxes. It's about 2 boxes tall and about 2 boxes wide, and represents atrial depolarization. Your PR interval is the SA to AV transit time for the heart. It should be between 3 and 5 small boxes long, and it should remain on the baseline. Your QRS complex, this is ventricular depolarization. It should be less than 0.12 seconds, and it can vary in shape and size, and we use various capitalized and lowercase letters to denote the appearance of that complex. The ST segment, the period between the QRS complex and the start of the T wave, is the pausing period before repolarization starts in the ventricles. Your T wave is ventricular repolarization. The normal duration varies, but the shape should be consistent. It should be an asymmetrical object in the same deflection as the QRS complex, with a soft slope upward and a rapid return to baseline, less than half the total height of the QRS complex. One key here is memorize the numbers. Don't just rely on the boxes. If you can help remember the mechanics and the math of this, it will make interpretation easier in the future. Learn what's normal. Focus on this image, learn the normal approaches, because every dysrhythmia you will learn is simply a deviation from normal. Trust the math and learn the numbers. And remember, just as we mentioned in the last lecture in this series, interpretation is much art as science, and practice will go a long way in helping you hone your art and apply the science to this process.